Good morning. Today, we are going to address a fundamental question in high-speed circuit design. Why LDO? We'll explore why low drop-out regulators are not just a component, but a critical design choice for ensuring the performance and reliability of modern data communication systems. The core challenge we face is moving massive amounts of data between chips quickly and efficiently. Traditional pair bus, think of wide multi-lane highways, are bulky and expensive. The solution is the SerDes, or serializer, which converts this wide parallel data into an ultra-fast serial stream, much like funneling a highway into a high-speed train tunnel. This is the technology that powers everything from USB and Ethernet to the backbone of the Internet. Inside a SerDes, we have several key blocks: the transmitter, the receiver, and the timing circuits, the PL and CDR, which are the heart of the system. A critical issue is that these sensitive analog timing circuits share the same sequence and package as noisy digital logic. This creates multiple pathways for noise to couple into the analog rail through mechanisms like IR drop and ground bounce, directly threatening the signal integrity of our high-speed signals. This is where the on-chip LDO comes in. Its primary job is to act as a shield. It isolates the critical timing circuits, the PL and CDR, from all the digital and power supply noise. It achieves this through two key features. First, a high power supply rejection ratio, or PSR, which actively filters out noise and prevents it from becoming timing jitter. Second, it provides a fast transient response, ensuring the voltage remains stable even when the current demand changes rapidly. All of this is achieved with a minimal voltage drop, typically just 50 mV to 200 mV. So, what happens if we skip the LDO? We create a direct chain reaction from noise to failure. Supply ripple directly modulates the frequency of our timing oscillator and shift the voltage threshold of our data comparator. This immediately increases jitter, which crosses the data eye, raises the BL rate, and can even destabilize the equalization circuits. The result is a fragile link with narrow margin, prone to immediate and hard to diagnose failure. The modern solution isn't to put an LDO on everything, but to use it in an intelligent way, like hybrid approach. We partition the power delivery by sensitivity. A single shared high-performance LDO is used for all the sensitive analog blocks. The less sensitive logic rail are then powered by more efficient solutions, like simple RC filter or switch capacitor converters. This strategy, combined with careful ball and package core design for clean ground paths, give us the best of both worlds: high performance where it matters and high efficiency everywhere else. Let's look at a practical number. The power overhead of an LDO is actually quite small. Because the voltage headroom is only 50 to 200 mV and the analog load current is low, the power loss is typically in milliwatt range, a tiny fraction of the chip total budget. In return, we aim for a PSR greater than 40 to 60 dB, especially in the range of switching noise is dominant. This gives us a microvolt level clean supply, which is the key to achieving a stable, high-performance link. Now, are there exceptions? Yes, but they are rare. You could potentially skip on-chip LDO if you have an exceptionally clean power delivery network. But this is extremely expensive and difficult to engineer. The other major exception is the move toward most digital receivers that use an ADC and DSP. These are most tolerant to noise, but even they still require clean voltage reference for their ADC. In either case, skipping the LDO is a significant risk that requires extensive lab validation to ensure you don't face late-stage failures where noise assumption breaks. This brings us to a simple practical rule of thumb. Getting rid of the on-chip LDO is common and a smart move for system cost and efficiency. But removing on-chip LDO in a high-speed service is rare and very risky. The golden rule is this: any timing critical analog rail needs an LDO or equivalent isolation filter, and you must always validate this with measurement by injecting ripple and stretching the link across all process, voltage, and temperature corners. Here are the summary images showing you why LDO is needed. Basically, we keep on-chip LDO to isolate sensitive analog circuits, which directly lead to power jitter and a low bit array. We use hybrid power scheme to optimize for both performance and efficiency. The trade-off is clear and overwhelmingly positive. A tiny milliwatt cost for massive gain in signal integrity. The next step in any design should be to specify this PSR and noise target. Plan the layout and decoupling carefully and prepare for rigorous supply injection tests to validate the final design. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback. I appreciate your comments down below. Lastly, please share the video with the people who may be benefiting from it.